picture a supercomputer. Like
Yeah.
if you're listening to this right now, you're probably visualizing a massive, highly sterile room.
Oh, absolutely. Rows and rows of blinking server racks.
Exactly. Aggressive air conditioning just sort of humming in the background. Miles of perfectly organized fiber optic cables.
Yeah, we really associate advanced computing with, well, total isolation from the natural world. I mean, building a machine that powerful usually requires a massive electricity bill just to keep the whole system from melting down.
In a totally pristine environment, right, to keep dust or moisture from shorting out the motherboards.
Exactly. We treat computing like it requires absolute sterility. Like, to process data, we have to isolate it from the messiness of biology.
But what if the ultimate supercomputer doesn't actually need an air-conditioned room?
Right.
What if it's already running, like, right beneath our feet in the wet, muddy, chaotic dirt of a rainforest?
It is a massive paradigm shift. I mean, it requires moving away from the idea that we have to build our computational infrastructure from scratch.
Yeah.
And moving toward this realization that the biosphere itself has been computing for billions of years. We just, we haven't had the right plug to tap into it.
Okay, let's unpack this, because the source we are diving into today is truly mind-bending.
It really is.
We've got our hands on a really fascinating academic thesis chapter. It's Chapter X, and it's titled From Biocell to Biome.
Authored by Martín Gutiérrez Guerrero.
Yes, exactly. It's part of the Novi Amazonia project down in Costa Rica. And the premise is wildly ambitious.
Ambitious is an understatement.
Right. He is proposing that humanity can basically build an interface to connect with a planetary-scale quantum analog computer that already exists within Earth's biosphere.
And the goal isn't just to, run simulations or crunch numbers.
No.
The objective is to essentially create a global AI-boosted immune system against extreme environmental pollution.
Which is just wild to think about.
It is. What makes this text so compelling is the fundamental shift from human-made sort of top-down nanotechnology to biologically guided architecture.
Right. It forces us to ask why we've spent decades trying to out-engineer nature when we could just, well, collaborate with it.
Exactly.
Like doing it with coffee. That's the part that really hooked me.
Yeah, that's the kicker.
We are merging coffee farming, artificial intelligence, and quantum mechanics.
It sounds like science fiction.
It really does.
Oh.
So our mission for this deep dive is to figure out exactly how you upcycle everyday agricultural waste into a literal interface for a planetary supercomputer.
Well, to understand how we compute with a forest, we first have to look at the physical hardware that makes it possible.
Right, the actual physical stuff.
According to the thesis, the foundation of this entire system relies on something called 3D biogenic graphene, or 3D Bio-G.
And the origin of that material is surprisingly mundane, right?
Surprisingly so, yeah. The earlier chapters of Guerrero's thesis prove that taking the pruning waste from coffee Arabica,
Literally just the leftover branches from coffee plants.
exactly, just the waste, taking that and pyrolyzing it at 1100 degrees Celsius creates something remarkable.
Baking it at super high heat.
Right. When that biomass is baked at extreme temperatures under controlled conditions, the organic matter burns away.
Okay.
And it leaves behind a microscopic carbon structure that is incredibly conductive.
So it turns into this highly efficient conductor.
Yes. In the lab, they proved this worked beautifully inside a 2,500 cubic meter bioreactor.
But a bioreactor is a closed system.
Right.
And the ambition of this chapter is to take that conductive coffee carbon out of the lab and map it onto an entire ecosystem.
Which is a massive leap.
Huge. The author describes creating a conductance graph. Now, any network needs nodes and wires, right?
Naturally.
So if we look at the soil, the nodes are biological clusters, specifically exoelectrogenic bacteria like geobacter.
Yeah, these are bacteria that naturally produce electricity. They're basically breathing out electrons as a byproduct of their metabolism.
Breathing out electrons, that's so cool.
It is. So if the bacteria are the nodes generating the current, the existing routes for electron transfer in the soil serve as the wire.
Like fungal hyphae.
Exactly, the underground mycelial networks, or even the vascular systems of the plants themselves, the famous wood wide web.
Right. But the text points out a major flaw in relying solely on the Wood Wide Web.
It does.
Natural systems, while brilliant, aren't perfectly optimized for long-distance, high-speed electron transfer.
Yeah.
They have bottlenecks.
Yeah, areas of high friction. or what the thesis calls high interfacial tortuosity.
High interfacial tortuosity, basically where the native electron transfer is incredibly inefficient.
Right, and those bottlenecks are exactly where the biohardware comes into play.
Okay.
The thesis introduces the Bio3D Phyto-Cell.
The Bio3D Phyto-Cell.
Yeah, this is a microscopic unit of that high-purity coffee carbon we talked about.
Right.
Inserted directly into these existing natural networks, it acts as a low-resistance node right where the network struggles the most.
So it's basically like inserting a highly conductive microscopic stent into the Wood Wide Web.
That's a great analogy.
Like you were giving a dial-up forest a fiber optic upgrade without having to rip out and replace the original wiring.
Exactly. That microscopic stent approach is elegant because of its humility. It complements the ecosystem rather than overwriting it.
Which is usually how we do things.
Right. Traditional nanotechnology often tries to build an artificial replacement from scratch.
Yeah.
But here, the carbon scaffolding just bridges the biological gap. It provides a highly conductive pathway exactly where the natural system needs it.
Allowing the native bacteria to interface with the roots and fungi almost seamlessly.
Perfectly seamlessly, yeah.
Okay, so we have these microscopic coffee graphene stents sprinkled throughout the soil, bridging the gaps in the natural electrical grid.
Correct.
But the physics detailed in this chapter go way beyond simple electricity moving down a wire. The thesis explicitly states the physics here rely on quantum tunneling.
Yes. And this is where the text gets incredibly dense.
It really does. It brings up tunneling governed by the WKB approximation and Marcus theory. Honestly, these concepts are intimidating.
They are definitely heavy physics concepts.
Like, I think of quantum tunneling happening in delicate laboratory setups with lasers and absolute zero temperatures. Not in the dirt.
It sounds totally paradoxical, I know. Let's break those terms down so we understand the mechanics of what is actually happening in the soil.
Please do.
So, Marcus theory essentially explains how electrons jump between molecules. Think of it as calculating the exact amount of energy an electron needs to leap across a microscopic hurdle.
Okay, a microscopic hurdle.
Right. And that energy requirement is called the reorganization energy.
Reorganization energy.
Good.
Got it. And the WKB approximation.
That is the mathematical formula used to calculate the probability that the electron will actually make the jump.
Probability. Okay.
Because in quantum tunneling, an electron doesn't climb over the hurdle, it passes directly through it, like a ghost walking through a solid wall.
Oh, wow.
Yeah. The WKB approximation calculates the chance of that ghost successfully making it to the other side.
Okay, so for that ghost to make the jump, the thesis states a very strict physical requirement. The distance between the biological film, the bacteria or the root, and the carbon substrate must be less than 1.5 nanometers.
A very, very tiny gap.
Right. If you achieve that microscopic proximity, the electrons tunnel through the barrier. But let me push back on the practicality of this for a second.
Sure.
In the controlled lab bioreactor, the reorganization energy was stable. The text notes that resistance dropped from 2,000 ohms down to between 2 and 15 ohms.
A massive stable drop, yeah.
But a real forest floor is highly unpredictable. You've got varying soil moisture, different ion concentrations, roots releasing random chemicals.
That's messy.
Very messy. How on earth does a delicate quantum state survive in messy, wet, acidic soil without completely collapsing?
Well, the environment you just described, the wet, chaotic soil, is exactly what separates this applied planetary engineering from pure theoretical physics. The answer to how the quantum state survives lies in what the author calls a massive separation of timescales. We have to look at the sheer speed of these processes.
Geez, okay.
The quantum tunneling, that electron jumping the gap, happens almost instantaneously. We are talking femtoseconds to picoseconds.
A femtosecond being a millionth of a billionth of a second.
Right. It's incomprehensibly fast. Now compare that to the plant's biological responses.
Like growing.
Exactly. When a plant changes its sap flow or grows or reacts to a change in soil acidity, those processes take hours or even days.
Oh, I see.
Yeah, the plant and the electron aren't operating in the same temporal universe.
Which means the femtosecond quantum reactions are so fast, they act as instantaneous sensors for the slower-moving environmental changes.
Precisely. That incomprehensible speed is the whole secret to making this work.
Okay.
If a storm washes a sudden pulse of acidity into the soil, the quantum tunneling rate fluctuates instantly in response to that new chemical reality.
So the system doesn't try to protect the quantum state from the macroscopic mess.
Not at all. The environment modifies the boundary conditions of the quantum tunneling. And because the system is measuring that tunneling, it is effectively measuring the environment in real time at a molecular level.
So the noise isn't ruining the signal. The noise IS the signal.
Exactly.
The quantum tunneling is just taking billions of instantaneous snapshots of the chaotic environment.
Yes, billions of them.
But wait, if this biological network is taking billions of snapshots a second across thousands of hectares of forest floor, that creates a massive data problem.
A staggering amount of data.
Right. A human operator couldn't parse a fraction of a second of that data, meaning this biological network is entirely useless without an autonomous brain to filter it.
Yeah, running a system of this complexity manually is physically impossible. This necessitates the next massive component of the architecture.
The AI layer.
Yes, the SBAI, or Autonomous Intelligent Bioquantum Systems. The AI serves as the management layer, utilizing two primary tools.
Okay, what are they?
First, graph neural networks, or GNNs, and second, physical layer transformers.
So if the graph neural network is looking at the macro health of the forest, it must be taking all those nodes, our bacterial and fungal connection points, and mapping the overall connectivity.
Exactly. The GNN acts as the big picture diagnostic tool. It monitors the vast web of nodes.
Like a bird's eye view.
Right. If a specific cluster of nodes suddenly drops in conductance, the GNN identifies that anomaly. It knows there's a blockage or biofouling, or that the local bacteria are exhausted.
Long before those microscopic issues manifest as macroscopic problems for the wider ecosystem.
Precisely. It catches the problem early.
But the GNN still doesn't solve the chaotic noise of the dirt. That must be what those physical layer transformers are doing, filtering out the static.
You nailed it. They handle that exact signal-to-noise problem. A forest floor is full of high-frequency thermal noise.
Just from heat.
Yeah, just the random, meaningless jitters of molecules reacting to heat. The transformers analyze the femtosecond electrical fluctuations and filter out that meaningless thermal jitter from actual, meaningful environmental signals.
Like the arrival of a heavy metal contaminant.
Exactly.
The thesis makes a really crucial distinction about the AI's role here, though. It is very strict that the AI does not alter the laws of quantum physics.
Right, it's not magic.
It isn't changing the mass of an electron or manipulating Planck's constant. The text says it only regulates macroscopic boundary conditions.
Yes.
But how does code actually manipulate dirt? Software can't magically tell an electron to move left. What is the physical mechanism of this intervention?
Well, it doesn't use a tractor beam to move electrons, you're right. The AI is connected to physical macroscopic infrastructure at the boundaries of these ecosystems.
Okay.
Think of it like a sound engineer at a concert adjusting the mixing board. The engineer isn't playing the guitars or singing the vocals.
They're just managing the sound.
Exactly. They are adjusting the acoustic environment, the levels, and the feedback so the signal cuts through the noise.
Oh, I get it. So applied to a wetland, the AI might actuate microvalves regulating water flow or trigger automated dispensers that adjust local soil alkalinity.
That's exactly it. By tweaking the flow rates of water or the local electrochemical balances, the AI optimizes the environment to favor certain natural reactions over others.
Okay.
The physics of the electron tunnel remain pure natural physics. The AI simply decides which macroscopic gates to open or close to best utilize the energy the natural system is already producing.
Like, think about the smart thermostat in your house, right? It doesn't physically push hot air through your vents.
Right.
It reads the environment and triggers the furnace when the temperature drops. The SBAI is doing the same thing for the forest floor, but on a mind-boggling scale.
Mind-boggling scale is right.
And that leads us to the real-world applications. We have the biogenic graphene hardware acting as microscopic stents. We have the quantum tunneling sending data. And we have the AI adjusting the physical boundaries to manage the flow.
All working together.
So what does this planetary computer actually do to build an immune system against contamination? Let's look at waterways first.
Sure. River systems and estuaries are highly vulnerable to industrial runoff. The text details how the system detects toxins from illegal mining.
Specifically elements like hexavalent chromium and arsenic, right?
Yes. But detection is only the first step. The bacteria in the network are constantly producing surplus electrons.
Okay.
Once the transformers filter the noise and identify the heavy metal, the AI adjusts local boundaries to direct those surplus electrons toward the contaminant.
And sending an electron to a heavy metal fundamentally changes its chemistry.
It does. It chemically reduces the heavy metals, changing their valence state.
What does that mean practically?
This transforms them from a dangerous soluble form that spreads easily in water into an insoluble solid.
Wow.
Yeah, the toxic metals effectively drop out of solution and become physically trapped right there in the carbon matrix of the phytocell before they can flow downstream.
It neutralizes the threat in place.
Exactly, in
And
place.
while tackling issues like agricultural eutrophication, where excess fertilizer basically chokes a waterway, the system somehow generates energy.
Yes, it does.
The thesis cites a generation of 2 kilowatt-hours of energy per cubic meter treated. That's amazing.
It's because the bacteria produce more electrons than are needed for the remediation. The excess current can be harvested.
So the system cleans the water and powers its own sensors simultaneously.
Exactly. It's self-sustaining.
Okay, moving from waterways to the forests, the system becomes even more proactive. The text describes using the graph neural network for kinetic monitoring.
Right.
If the GNN has mapped the entire fungal network and a toxic leaching front starts moving through the soil from an industrial spill,
Yeah.
the system doesn't just watch it spread.
No. The GNN tracks the speed and trajectory of the toxin. It calculates exactly where the contamination is going.
Predictive data.
Right. With that predictive data, the AI can prioritize remediation in that specific path, marshaling the bacterial electron flow to build a biochemical wall in the soil.
A biochemical wall.
Yeah, neutralizing the toxins before they ever reach the groundwater.
It's like predictive medicine for the ecosystem.
Exactly.
But the most staggering application in this chapter, I think, is how it handles radioactive waste.
Oh, this part is incredible.
Specifically for the massive mining operations in Latin America. The thesis states that the system can direct the network's electron surplus to intercept a radioactive plume of soluble uranol,
Yes.
reduce it into insoluble uraninite, and physically confine the radiation.
Mm-hmm.
We are literally using a forest's native bacterial electrical grid to physically freeze radioactive waste in place before it spreads.
Well, orchestrating the native grid is a better way to look at it. The SBAI doesn't change the thermodynamics of uranium reduction.
Uranium chemistry remains uranium chemistry.
Exactly. What the AI does is perfectly optimize where the natural system directs its biological energy.
Okay.
It senses the radioactive flume, calculates its geometry, and adjusts the local boundaries to marshal the excess electrons from the surrounding microbial life to that exact location.
Just overwhelming the plume with electrons.
Right. The surplus electrons change the valence state of the soluble uranol, forcing it to precipitate out as solid insoluble uraninite.
Locking the uranium in the carbon matrix.
Yes. It optimizes the spatial deployment of the forest's own defense mechanisms.
The scale of that intervention requires a total shift in how we view technology, which brings us to the philosophical core of this whole thesis.
It's a beautiful way to frame it.
The author, Martín Gutiérrez Guerrero, summarizes this approach as science with hands in the earth and eyes on the stars.
I love that quote.
Me too.
Yeah.
For so long, human engineering has treated biology as an obstacle. We thought to build high tech, we had to pave over the natural world.
Yeah, modern engineering has been defined by the assumption that a constructivist, top-down approach was the only path forward.
Like building microscopic machines from rare earth metals in sterile clean rooms.
Exactly. Nature was considered too messy, too chaotic to be useful for precision computing.
But this thesis argues that nature's architecture, like the vascular stem of a humble coffee plant or the mycelial network of a forest floor, has already solved the thermodynamic problems we struggle with.
It really has.
And it does it at a remarkably low cost. The text notes this entire bioremediation system can be implemented for just $5 to $15 per square meter.
Democratizing planetary scale remediation is perhaps the most revolutionary aspect of the text.
Totally.
It proves that true high technology doesn't have to be manufactured in a billion-dollar facility. It might literally be growing in your garden right now, waiting to be upcycled and connected.
It fundamentally changes that image we started with. The ultimate supercomputer isn't a sterile room full of blinking servers.
No, it's not.
The supercomputer is the wet dirt, the pyrolyzed coffee plants, the fungal threads beneath our feet. We've spent decades trying to build machines to save the planet, when the planet itself is the most advanced machine we could ever hope to access.
We just needed the humility to learn how to plug into it, to stop treating the biosphere purely as a resource to be extracted,
Right.
and start treating it as a complex network to interface with.
Which leaves us with a final, really profound thought from the conclusion of the chapter. The text states that the biosphere has been computing for billions of years, right? Processing massive amounts of data, reacting to environmental shifts, optimizing life on a global scale.
Oh, yeah.
And we are just now, finally, building the interface to listen in.
Yeah,
Mostly just so we can clean up our own toxic messes.
exactly.
But if the Earth is already functioning as a massive quantum analog neural network, constantly analyzing billions of femtosecond snapshots of its environment, what else might this biological computer be processing right now that we haven't even thought to ask it yet?